Guided Notes Unit 10. This is part 3 of our video. We're going to be talking about still differences in means for our hypothesis testing, but it's a bit different this time because we're talking about paired data. So remember, paired data would be if I weighed everyone in our class and then we all went on a diet where the only thing we drank was Mountain Dew, and then later we all weighed ourselves again, and then we compared the average of our weights at the beginning and compared it to our average of our weights at the end. Now this is paired data because your weight before and your weight after is paired together. So we would be recording two values of two values of the same quantitative variable, weight, for each individual. But it's also possible to do this for each pair of similar individuals. So if I ranked us, this would be horrible, but if I ranked us by weight from greatest to smallest, and then I paired up the two largest, and then the next two largest, and the next two largest, and the next two largest, and then randomly assigned one of you to drink only Mountain Dew, and then the other person to just drink regulars, what they regularly would drink, then I would still have paired data, and I would have each pair of similar individuals for these two different treatments that we're comparing. So when we do this, we are going to, what am I writing out? I think I'm on the wrong page. So when we do this, we are going to start by finding the difference within each pair or within each individual. There we go. So we're going to find the difference within each pair, and then we'll calculate its average and its standard deviation. So we'll find the difference, and then we'll find the average, the sample average of the difference, the sample standard deviation of the difference. So when the paired data come from a random sample or from a randomized experiment, we want to perform a significance test about the true mean difference mu sub diff. The null hypothesis usually will just say that this average difference for the population is some hypothesized value. Again, we're going to focus on when this is 0, so we're looking for the null hypothesis saying that the average difference is 0. The alternative will just be what we expect, greater than 0, less than 0, not 0. The conditions are the same as when we came up with the confidence interval for this average difference. So we got to make sure that the paired data come from a random sample from the population of interest. So you guys as a class don't represent a random sample, so my example is kind of crappy because it already fails the first condition. It could also be a randomized experiment. So within the class, I could randomly assign you to the two different treatment groups, and that would make it better. I wouldn't be sampling without replacement in that case, but if you ever are sampling without replacement, the number of differences, not the number of total things you measure, but the number of differences need to be less than 10% the population number of differences that would exist. And then you still have to pass the normal large sample condition. So your population distribution needs to be normal. This could also be the distribution of differences in the response to the treatments. The true distribution needs to be normal, or your sample size needs to be large, meaning your number of differences needs to be at least 30. And if not, just sketch it and see what it looks like. So if you meet these conditions, we are going to be doing a one sample t-test, which we've done before, but now it's for a mean difference. Sometimes this is called a paired t-test for a mean difference. They're interchangeable because you are looking at paired data for both of these. The standardized test statistic should look really familiar. We are going to use a t-test statistic and a t-distribution. We're going to take the average of the differences that we find, subtract it the parameter, and we're assuming it's 0 until we have convincing evidence otherwise. And then we're going to divide by the standard error of our statistic, which remember is when you take the sample standard deviation, which is of the differences here. We don't know the population. And we're going to divide by the square root of our sample size, which again is the sample size of differences, however many differences we'd have. Then we're going to find the p-value using our t-distribution, and our degree of freedom is the number of differences minus 1. So that's what we're going to do in this first example. They designed an experiment to study the effects of caffeine withdrawal. So they recruited, because you asked for that, Eloise. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from caffeine, cola, anything that has caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which subjects took these different pills was randomized. At the end of the 2-day period, a test for depression was given to all 11 subjects. The researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So the table display the depression scores. High scores show more symptoms of depression. So we have the subjects so it's the same subject. Sometimes they took one pill, and another period they took the other pill. So I'm just going to start by stating our hypotheses. So we are trying to see if we have evidence against there being no difference. So the average for the population like this is 0. But we're testing a claim, and it specifically says, does it increase the depression score? So that means, are these average differences a positive number? So what I mean by that, you can find an example of that. So it's, the order of subtraction matters also. So before I get into an example, I'm going to define mine as placebo minus caffeine. If you want to define it as caffeine minus placebo, state that and then use that. But if I do placebo minus caffeine, you'll notice that this first subject, when I do that order, I'm getting a positive number, which means when the person was away from caffeine, it increased their depression score. So that's what I'm saying by it's increasing. So I'm just I oftentimes will use an example out of the data to make sure I have the order correct. And I'm going to define that mu sub diff is the true mean difference in this particular order on this depression test for subjects like these. There was no significance level stated, so I'm just going to say, because it wasn't given, I'm just going to set alpha being 0.05. I'm planning to, again, do a paired t-test for the mu sub diff. And you could also say a one sample t-test for the mean difference. Interchangeable. So that's what I'm noting in my plan. And I passed the random condition because it says they randomly assigned the treatments of placebo then caffeine or caffeine then placebo to the subjects. And I don't know the shape of the population distribution. I do have small sample sizes, but if I look at the histogram of these differences, it doesn't show me anything that's an outlier or dramatic skewness. So I'm just going to note that. So it's reasonable, it's plausible to think this came from a normally distributed population because I don't have any outliers or strong skewness. So I've passed my conditions. I can jump now to actually doing this. So I need to calculate the differences first. So I could do this by hand. Subtracting is not overly difficult, but you could also use your calculator. Again, sorry, I'm going to be showing how to do this for those of you with TI 83, 84 calculators. Everybody else, follow along and then try and look it up on your own calculator. So I'm just going to enter in the data. So I'm going to hit Stat, Edit, and because I'm doing placebo minus caffeine, I'm going to enter in the placebo numbers first. So that would be the 16, 23, 5, so on and so forth. And then I'm also going to do the same thing for the caffeine. So again, I want the difference. I don't want to subtract these by hand. I would like it to take every value in L1. So I've scrolled up, so L3 is highlighted. And I typed in second number 1 for L1. And I'm subtracting L2, second, then the number 2. So I'm getting the difference. 16 minus 5 is in fact 11. It is not hard to do that by hand, but I'd rather my calculator do it for me. Now I want the average of these numbers and the standard deviation of these numbers. So I'm just going to run my one variable stats, but tell it I need it to use the list in L3. And I think frequency list sometimes just says 1, but I don't want to have a frequency list. I have a bunch of differences in L3. I want to use that. So I'm getting an average difference of 7.364-ish and a standard deviation for my sample of 6.918. So these are the two numbers that I'm going to use to calculate our standardized, sorry, I didn't know how long that was on. These are the two numbers that I'm going to use for my standardized test statistic. So again, that was from, that was from our one variable stats from the values in L3, which was the difference in L1 and L2. So I need to actually write down those numbers. I can't just exclusively do this in my calculator. So I'm going to note that my sample average difference, wait for it, so x bar sub diff was the 7.364. My standard deviation for my sample of differences, 6.918. And the sample size of these differences, there were 11 differences for those 11 people. So you calculate your test statistic. So I'm going to take my sample difference minus the parameter, so I'm assuming it's 0. I'm going to divide by my standard error of the statistic, which is the standard deviation of those differences over the square root of the number of those differences, which gives me 3.53. We're going to use a t-distribution. The degree of freedom is the number of differences minus 1, so we'll have 10 degrees of freedom. This is a right-tailed test based off of our hypotheses. So our p-value, found by TCDF, I'm going to go from 3.53 on up. When I do that, what did I get? 0.0027. Quick side note, I did not have to do it this way. I did not have to calculate those by hand. So back to my calculator. I could have just said that I'm about to run a t-test. Not a two-sample t-test because this is paired data. That's when you just use your regular t-test. And I actually have data. So you could just highlight data. The null hypothesis has 0 in it that we're comparing it to. This is the parameter value you're assuming to be true. Mine is currently in L3, so I'm going to put that in. I'm going to ignore the frequency. It is a right-tailed test, and I'm going to calculate it. You'll notice the exact same standardized test statistic. It's still approximately the same p-value, and it doesn't state degrees of freedom on this one, but you can find that yourself. So you could do this yourself rather than going through the steps of all of this. It should give you approximately the same, especially if you know using technology I got. As always, just explain how you got what you got. And then we're going to make a conclusion. This p-value, pretty small. So I'm going to say our p-value 0.0027 is smaller than the level of alpha that I chose. Smaller than any reasonable alpha. So we are going to say that we can reject. You're always making a decision first on your null hypothesis. We have reason to think the thing that I was thinking is true isn't true anymore. So we're going to reject the null hypothesis. Oh, I just now read what I'd wrote. Give me a second. Because the p-value of 0.0027 is greater than alpha. Now I can reject the null here. That makes more sense. And I can say that we have convincing evidence for the null. Sorry, we have convincing evidence for the alternative. So we have convincing evidence that caffeine withdrawal increases depression test score on average for subjects like these in the experiment. Again, only like the ones in the experiment, not for the whole population because we didn't draw from the whole population. So really similar process as before. There's another one on here that I will put online for our answer key. But the main issue that students run into is knowing when you're supposed to do what. So the last thing on here. If you have independent random samples or two groups in a randomized experiment, as long as the conditions are met, that's whenever you are doing your first test, your first type of test here of the two sample T procedures. If you have paired data, so the same person does something twice, or similar people compare the results. If you have any type of paired data, that's when you use the paired T procedures we just went through. So for these ones, I just want to know which one you're supposed to be using and why. So part A, before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fins that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove old fins on average. So key thing here, we're not talking about proportions here, it's definitely talking about averages. 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or reverse of that. The time to remove each fin is recorded for every diver. So, because we have, pretend you're one of these divers. You're wearing one fin on one foot and the other on the other. You are one person with two different variables that are being compared. So we are pairing your left foot with your right foot. This is a paired T procedure. So the data comes from two measurements of the same variable, the time to remove the fin for each diver. For part B, to study health of aquatic life, scientists gather a random sample of 60 white piranha fish from a tributary of the Amazon River during 1 year. The average length of these fish was compared to a random sample of 82 white piranha from the same tributary a decade ago. One key thing that should kind of let you know that this is not paired data, you can't pair unequal groups. So for example, in one of my stats classes, there's 22 kids, the other there's 15. There's no way for me to pair a 1-to-1 ratio. And if you don't have 1-to-1, you can't have paired data. So this is a two sample T procedure. He's asking you to play hide and seek. Procedure. So again, the data come from independent random samples of white piranha in 2 different years. That's why it's this. And the last one, can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are supposed to deter shark attacks. To test this idea, she fills 2 identical drums with bait and covers one in the standard black neoprene wetsuit and the other in the new suit. Over a period of 1 week, she selects 16 2-hour time periods, randomly assigns 8 of them to the drum in the wet black suit. The other 8 are assigned to the drum with the new suit. During each time period, the appropriate drum is submerged in the waters that sharks frequent, and the number of times a shark bites the drum is recorded. This one's a little trickier because these sample sizes are identical. So we really need to ask ourselves, do we have 2 measurements of the same variable? Do we have each individual happening twice? Or do we have 2 independent random samples, or in a randomized experiment, 2 groups? So since the data comes from 2 groups in a randomized experiment, so each group has 8 time periods with the drum of a specified wetsuit. Because of that, this is a 2 sample T procedure. We're not just making some comparison of this one drum with these 2 things, or these 2 similar drums. We're not pairing them in any way. We just have these 2 groups that happen to be the same size and then making comparisons. So if and when you have questions, email me your questions. I am not getting very many emails, and this is not necessarily super easy work, so that tells me you guys are either half-assing it, or you're maybe asking each other questions, which is fabulous, or you're just kind of waiting